Welcome to Suresh Bhatt classes. We are going to study quantitative aptitude video topic numbers. Let us start the topic. Numbers are classified as 1. Natural number usually denoted by n. These numbers or numbers used for counting, which are 1, 2, 3, 4, 5 and so on, are natural numbers. Then second comes whole numbers, usually denoted by W. All natural numbers along with 0 form a set of whole numbers, and these are 0, 1, 2, 3, 4 and so on are whole numbers. Any natural number is a whole number, and 0 is whole number and not a natural number. Then point 3 is integers, usually denoted by Z. It consists of natural numbers plus 0 plus negative counting numbers form a set of integers. It starts from minus infinity and continues to minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on, and these are integers. Now positive integers, which start from 1, 2, 3, 4 and so on. Negative integers are all these with minus sign, that is minus 1, minus 2, minus 3, minus 4 and so on are negative integers. And 0 is neither positive nor negative. Integers are further classified as part 1, even numbers. Number divisible by 2 is called even number. All numbers ending with 0, 2, 4, 6, 8 are even numbers, like 20, 32, 44, 56, 68 ending with 0, 2, 4, 6, 8 are all even numbers. Second is odd numbers. Number not divisible by 2 is called odd number. All numbers ending with 1, 3, 5, 7 and 9 are odd numbers. For example, 21, 33, 45, 57, 69. All other such numbers which are ending with 1, 3, 5, 7 and 9 are odd numbers. Part 3 is prime numbers. A number divisible by only 1 and itself is called a prime number. And examples for prime numbers are 2, 3, 5, 7, 11, 13 and all those numbers which are divisible by 1 and itself are prime numbers. Fourth, composite numbers. Natural numbers greater than 1 which are not prime numbers are called composite numbers. 4, 6, 8, 9, 10 and many other numbers are composite numbers. Further, we can say that the numbers which has factors other than 1 and itself are composite numbers, as 4 has the factor 2, 6 has the factor 2 and 3, 8 has the factors 2, 4, 9 has the factor 3, 10 has factor 2 and 5, and all such numbers which has other than 1, there is a factor of that number is a composite number. To remember, part A, 1 is neither prime nor composite number. B, 2 is only even prime number. And C, there are 25 prime numbers between 1 and 100, which are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89 and 97. These are total 25 numbers which are in between 1 and 100. Part 5, coprimes. Any two natural numbers A and B are co-prime if their HCF is 1. For example, 4 and 5, 4 and 7, 4 and 9, 7 and 9, 9 and 11, 9 and 13. These are, and many more such numbers are co-primes. Individual may be a composite number, but together they have only one common factor, which is 1, or HCF of these numbers is 1. Therefore, these are called co-primes. Further, in the number system, category 4, rational numbers, usually denoted by Q, a number which is in the form of P upon Q or P over Q, where Q is not equal to 0 and P and Q are integers. For example, 1 upon 2, 3 upon 4, 5 upon 7 or 8 upon 11 are such numbers which are rational numbers. Fifth are irrational numbers. The numbers which are not rational numbers, that is, which cannot be written in the form of P upon Q, where Q is not equal to 0. For example, pi, under root 2, under root 3, under root 5 and all such numbers. Sixth is real numbers, usually denoted by R. All the above numbers included form a set of real numbers. It means that all irrational numbers and rational numbers included, which includes natural number, whole number, integers, rational number, irrational number, all these are included, form a number line, and it is called real numbers, or that line is called real number line. Complex number. 7 is complex number. The numbers represented by a plus ib, where a and b are real numbers and I equal to under root minus 1. This is imaginary number, and the examples for these numbers are 5 plus under root minus 8, 7 plus under root minus 4, 3 minus under root minus 5. Here 5 and 8 are integers, so 5 plus under root minus 8 can be written as 5 plus under root of minus 1 into under root 8, where 5 and 8 are real and minus 1 is imaginary. Together these two numbers, one part is real and other part is imaginary, is called a complex number. Here in this part of numbers, we are going to deal with real numbers. How to verify the given number is a prime number? Step 1. Find a natural number n whose square is just greater than the given number. Step 2. Test the divisibility of given number by all prime numbers which are less than n. Step 3. If the number is divisible by any of the numbers of step 2, then the given number is not a prime number. And if it is not divisible, then the given number is a prime number. We will learn this by few examples. The given example is, are the numbers 209 and 211 prime? So we have to solve this. We have to find the number n whose square is greater than 209 and 211, and that number is 15. The square of 15 is 225, which is just more than 209 and 211. And the square of 14 is 196, which is less than 209 and 211. So we'll choose 225, and the number which is 15 whose square is 225. Now we'll find all the prime numbers which are less than 15. So those numbers are 2, 3, 5, 7, 11 and 13. If the number 209 and 211 is divisible by any of these numbers, then the number is not prime. And if it is not divisible, then it is prime. So we test 209. 209 is odd number, so it is not divisible by 2. And the sum of the digits 2 and 9 is 11, so it is not divisible by 3. As it is not ending with 0 or 5, so it is not divisible by 5. So we will check whether it is divisible by 7 or not. On dividing by 7, we get 7 times 2 is 14, and subtracting 14 from 20 we get 6. We carry 9, and 7 times 9 is 63, and remainder is 6. So it is not divisible by 7. Now we test it for 11. 209 on dividing by 11. 11 times 1 is 11, and subtracting 11 from 20 we get 9. We carry 9 from the above, and 11 times 9 is 99. So this is divisible by 11. Hence 209 is not a prime number. Now we will test it for 211. As we know that the sum of the digits of 211 is not divisible by 3. So it is not divisible by 3. As it is odd number, so it is not divisible by 2. As it is not ending with 0 and 5, so it is not divisible by 5. Now we check it for 7. 7 times 3 is 21. We carry 1. And 1 is not divisible by 7. So 211 is not divisible by 7. Now we test it for 11. As the difference of sum of the digits at even places and odd places is not 0 or 11. So it is also not divisible by 11. Now we try it for 13. 13 times 1 is 13. And subtracting 13 from 21, we get 8. We carry 1, and 13 times 6, 78, and on subtracting 78 from 81 we get 3. Now it is not divisible by 13. So 211 is prime number, while 209 is not a prime number. This way we can verify the number whether it is a prime or it is a non-prime number. Test of divisibility of numbers. Numbers divisible by 2. Digits at unit place ending with 0, 2, 4, 6, 8. Then the number is divisible by 2. For example, 42, 66, 98 and 1124. These all digits are ending either with 2, 6, 8, 4. Hence these all numbers are divisible by 2. These all are even numbers. Number divisible by 3. Sum of digits is divisible by 3. Then the number is divisible by 3. And the example for it is 2376. The sum of the digit is 2 plus 3 is 5 plus 7 is 12 plus 6 is 18. And 18 is divisible by 3. Therefore, this number is divisible by 3. Number divisible by 4. If the last two digits of a number is divisible by 4, then the number is divisible by 4. And the example is 548. The last two digit is 48 is divisible by 4. If we divide 48 by 4, we get 12. Hence, it is divisible by 4. Therefore, 548 is divisible by 4. Number divisible by 5. The digits at units place is either 0 or 5. Then the number is divisible by 5. And the examples are 20, 50, 55, 65, 90. These numbers are either ending with 0 or ending with 5. Therefore, these numbers are divisible by 5. Number divisible by 6. The number is divisible by both 2 and 3. Then number is divisible by 6. Or in other words, all even numbers, the sum of the digits of that number is divisible by 3, then the number is divisible by 6. And the example for it is 42. The sum of the digits is 6, which is divisible by 3. Hence, this number is divisible by 6. 138. This is even number. Hence, it is divisible by 2. And the sum of the digit is 12. Therefore, this number is divisible by 3. Hence, it is divisible by 6. 246. The sum of the digits is 12. 2 plus 4 is 6 plus 6 is 12. And it is even number. So, it is divisible by 2 and 3 both. Therefore, it is divisible by 6. Divisibility by 8. If the last 3 digits of a number is divisible by 8, then the number is divisible by 8. And the number in example is 15856, 15,856. The last 3 digits is 856, is divisible by 8. If we divide 856 by 8, then it is divisible by 8, as on dividing 856 we get 107. Hence the number 15,856 is divisible by 8. Divisibility by 9. Sum of digits is divisible by 9, then the number is divisible by 9. The example given to us is 523476. Here the sum of the digits is 5 plus 2 is 7 plus 3 is 10 plus 4 is 14 plus 7 is 21 plus 6 is 27, and 27 is divisible by 9. Therefore, the given number is divisible by 9. Number divisible by 11. If the difference between the sum of the digits at even places and the sum of the digits at odd places is either 0 or divisible by 11, then the given number is divisible by 11. For example, the given number is 4318028. The digits at odd places is 4 plus 1 is 5 plus 0 is 5 plus 8 is 13. And digits on even places is 3 plus 8 is 11 plus 2 is 13. So both the sums are 13, and 13 minus 13 is 0. Therefore, number is divisible by 11. And on dividing by 11, we get the quotient equal to 392548. This way we can find the divisibility of the given number. Here it is not mentioned. The number divisible by 10, number which is ending with 0, is divisible by 10. Similarly, we can find the divisibility by 12. The number which is divisible by 4 and 3 is divisible by 12, and so on. Division algorithm. Dividend equal to divisor multiplied by quotient plus remainder. We can write n equal to p multiplied by q plus r, where n is dividend, p is divisor, q is quotient, and r is remainder. Here 0 is less than or equal to r is less than p. Important note: first, if r equal to 0, then n is completely divisible by p. It means that dividend n, when divided by divisor p, it completely divides the dividend n and there is no remainder left or remainder is 0. Second, if 0 is less than r less than p, it means that r is not equal to 0, then number n minus r will be completely divisible by p. If there is some remainder left, then if we subtract that remainder from the dividend, then the number obtained will be completely divisible by the divisor. Third, if 0 is less than r is less than p, then n plus p minus r will be completely divisible by p. If there is some remainder r, then if we add divisor to dividend and subtract the remainder from it, then the number so obtained will be completely divisible by the divisor. We will learn this by example. Our example is find the least number that must be part 1 subtracted from or part 2 added to the number 4132 to make it exactly divisible by 19. So we will solve this question. 4132 is divided by 19. So we will take 41 first, the first two digits of 4132. 19 times 2 is 38, and 38 when subtracted from 41 leaves 3. We carry 3 from the 4132. 19 times 1 is 19. On subtracting 19 from 33 we get 14 and we carry 2. 19 divides 142 for 7 times and 19 times 7 is 133. On subtracting 133 from 142 we get 9. Therefore 4132 minus 9 is equal to 4123, and 4123 is completely divisible by 19. So we have to subtract 9, which is the remainder, from the dividend 4132 to make 4132 completely divisible by 19. This was the part 1. Here n minus r is completely divisible by the divisor. Dividend minus remainder is completely divisible by divisor. Now as we know that 9 is the remainder, so what we have to do is n plus p minus r. So this is equal to 4132 plus 19 minus 9. This is equal to 4132 plus 10. This is equal to 4142. Thus, the minimum number which we have to add to 4132 is 10. And on adding we get 4142, which is completely divisible by 19. This way we can solve such type of questions. Our next example is find part A greatest and part B least 3-digit number exactly divisible by 17. First we will find the greatest 3-digit number which is divisible by 17. The greatest 3-digit number is 999 and we will divide this number by 17. 99, the first two digits, when divided by 17, we divide it for 5 times. So 17 times 5 is 85, and on subtracting 85 from 99, we get 14, and we carry 9 from above, and 149 is to be divided by 17. So it divides it for 8 times, and 17 times 8 is 136, and on subtracting 136 from 149 we get 13. So n minus r is 999 minus 13, we get 986, and this is completely divisible by 17, and this is the greatest 3-digit number divisible by 17. The question was asked, find greatest and least 3-digit number exactly divisible by 17. So the greatest 3-digit number is 986, which is divisible by 17. Now we have to find the least 3-digit number exactly divisible by 17. So least 3-digit number is 100, and that number must be close to 100. So we divide 100 by 17, and 17 times 5 is 85. We get 15 as remainder, and now n plus p minus r, that is our formula for solving such type of question, and here n is 100 plus p is 17, which is divisor, minus remainder is 15, and this is 100, and 17 minus 15 is 2, so 100 plus 2 is 102. So the least 3-digit number exactly divisible by 17 is 102. This way we can solve such type of question. Tips for finding remainder. The first tip is, if dividend n is not given in the question and is divided by two divisors x and y, where x is greater than y and x is multiple of y. Here it is important that x is greater than y and x is multiple of y, and remainder for divisor x is equal to a is given, and remainder for divisor y is equal to b is to be found, then case 1, when a is greater than y, then remainder b for divisor y will be remainder obtained by dividing a by y, and case 2, when a is less than y, then remainder b for divisor y will be a itself. We will understand these two cases by two examples, and we go to the examples. Example for case 1. When a number is divided by 585, the remainder is 43. What will be the remainder when divided by 13? Here the dividend is not given to us. The first divisor, which is x, is equal to 585, and for this divisor the remainder is 43. Now it is asked, what will be the remainder when it is divided by 13? So we will find it like this. First we will check whether 585 is multiple of 13 or not. So 585 divided by 13, 13 times 4 is 52, and on subtracting 52 from 58 we get 6, we carry 5, and 13 times 5 is 65. Thus the 585 is multiple of 13. Now to find the remainder when the unknown number, which was giving the remainder 43 on dividing by 585. So we have to find the remainder when that number is divided by 13. So we will divide the remainder 43 by 13, and 13 divides 43 for 3 times. 13 times 3 is 39. 43 minus 39 is 4. The remainder will be 4 when the unknown dividend is divided by 13. We will get the remainder 4. Here the x is equal to 585. Y is 13. Here remainder a is 43 and a is greater than y. Therefore, we divided a by 13 and remainder which we get is 4. Hope you have understood the tip for finding the remainder when dividend is not given and two divisors x and y are dividing the unknown dividend, where x is multiple of y. We go to the next example for case 2. Example for case 2. When a number is divided by 378, the remainder is 17. What will be the remainder when it is divided by 21? Here the dividend is not known to us. The first divisor x is given to us is equal to 378, and for this the remainder is a, which is equal to 17, and second divisor y is equal to 21. Now we have to find if that number is divided by 21, what will be the remainder? Here x is multiple of y. We can find it out. 378 divided by 21. 21 times 1 is 21. When subtracted from 37, we get 16. We carry 8. 21 divides 168 for 8 times. Thus the 21 is factor of 378, or 378 is multiple of 21. Now here a is less than y, that is 17 is less than 21. Therefore, when the dividend, unknown dividend, divided by 21, the remainder will be 17 itself. Thus the remainder will be a itself, which is equal to 17. This way we can find the remainder when the dividend is not given and the first divisor x is multiple of second divisor y. Tip second or tip 2 for remainder. If two numbers m and n are not given in the question, are both divided by one number x, leave remainder a and b respectively, then the sum m plus n when divided by x will give remainder r. Then case 1, r equal to a plus b minus x when a plus b is greater than x, and case 2, r equal to a plus b when a plus b is less than x. Here I am explaining this tip. If some unknown number m and n are divided by a divisor x, and m when divided by x leaves the remainder a, and n when divided by the x leaves remainder b. Now m plus n is divided by x. Then say the remainder is r. Then what will be the value of r? The value of r will be a plus b minus x. If a plus b is greater than x, if we add both the remainders a and b, then the net remainder when m plus n is divided by x will be a plus b minus x if a plus b is greater than x, if the sum of both the remainders a and b is greater than x, and if the sum of both remainder a plus b is less than x, then the net remainder will be a plus b. We will learn this by two examples, one each for each case. Example for case 1. Two different numbers when divided by the same divisor give remainders 23 and 19 respectively. When the sum of the given two numbers is divided by the same divisor give remainder 5. Find the divisor. Here the first remainder is 23, second remainder is 19. When the first number was divided by the divisor, the remainder is 23, and second number when divided by the same divisor, the remainder is 19. And when the sum of the two numbers when divided by the same divisor leaves the remainder 5, and it is asked to find the divisor, and we know the formula for the remainder is a plus b minus x, where x is the divisor, and we just put the value and find the value of x. So r is given to us is 5 is equal to 23 plus 19. A is 23 and b is 19, and minus x, which we have to find. Here x equal to 23 plus 19 is 42 minus 5, and 42 minus 5 is 37. Thus the divisor is 37. This way we can find the divisor. Here m is not given to us, that is first dividend, second dividend n is not given to us, and it is divided by some divisor leaves remainder 23, and second number when divided by the same divisor leaves the remainder 19. If m plus n, that is the sum of both the dividends, is divided by the same divisor leaves the remainder 5. Here the sum of both the remainder a plus b is greater than the divisor, because when m plus n is divided by x leaves the remainder 5, which is less than sum of a plus b. Therefore we can find the x easily by putting the value in the formula given in case 1. Hope you have understood the method of finding remainder in such case. Now we go to the second example where a plus b is less than x. Example for case 2. Two different numbers when divided by same divisor 43 give remainders 17 and 14 respectively. When the sum of the given two numbers is divided by the same divisor 43, what will be the remainder? Here the first remainder given to us is 17. Second remainder for the second number is given to us is 14, and we have to find the value of r, and the divisor given to us is 43. Here a plus b equal to 17 plus 14 equal to 31, and 31 is less than 43. That is a plus b is less than x. Therefore remainder will be equal to a plus b. Thus remainder r equal to a plus b, which is equal to 31. This way we can find the remainder when two different numbers are divided by the same divisor. Tip 3 for remainder. When two numbers m and n are divided by the same divisor x, give the same remainder r. Then number m minus n is completely divisible by divisor x. We will understand this by example. The given example is two numbers 365 and 449 on dividing by a divisor leave the same remainder. Find all possible divisors. As these two numbers leave the same remainder, therefore the difference must be completely divisible by the divisor. So the difference is 449 minus 365 is equal to 84. Now this number 84 must be completely divisible by the divisor. So we have to find the divisor, all possible divisors, and all possible divisors must be the factors of 84. So all the factors of 84, one digit factors are 2 and 8 and 4. The sum of the digit is divisible by 3, so the another number is 3. Then 84 is also divisible by 4. Then as it is divisible by 3 and 2, so it must be divisible by 6, and 84 is also divisible by 7. So one digit divisors are 2, 3, 4, 6 and 7, and two digit divisors are, as it is divisible by 3 and 4, so 12. This is also divisible by 2 and 7, so 14 is also one divisor. This is divisible by 3 and 7, so 21 is one of the divisors. Then it is divisible by 28, and this is also divisible by 42 and 84 itself. Thus the all possible divisors are 2, 3, 4, 6, 7, 12, 14, 21, 28, 42 and 84. This way we can find the all possible divisors by the property or tip for finding the remainders. Tip 4. When x plus 1 to the power n is divided by x, then remainder is always 1, where x and n are natural numbers. We can understand it by example. What will be remainder when 19 to the power 15 is divided by 18? And we can solve like this. 19 to the power 15 can be written as 18 plus 1 to the power 15. And when it is divided by 18, remainder will be always 1. Now we can find this by some more easy illustrations, like 19 to the power 2 is 361, and 361 when divided by 18, so 18 times 20 is 360, and remainder is 1. Similarly, 19 to the power 3 is equal to 6859, and when we divide it by 18, so 18 times 381 comes out to be 6858, and again the remainder is 1. This way 19 to the power, whether it is even or odd, when it is divided by 18 always leaves the remainder 1. This way the property is when x plus 1 to the power n is divided by x, then remainder is always 1, where x and n are natural numbers. We go to the next property. tip 5 for remainders. When x minus 1 to the power n is divided by x, then case 1, when n is even, remainder is 1. Case 2, when n is odd, remainder is x minus 1. Here the example given to us is, what will be remainder when x to the power 25 is divided by 16? The solution is 15 to the power 25 equal to 16 minus 1 to the power 25, and it is to be divided by 16. So the property or tip 5 is applicable here, because 15 can be written as 16 minus 1 and is to be divided by 16. And here n is 25, which is odd. Hence, on dividing by 16, by that property, the remainder will be 16 minus 1 equal to 15. And we can understand it by one easy example. 15 to the power 3, which is odd, is equal to 3375. And when we divide 3375 by 16, 16 times 2 is 32, balance is 1, we carry 7, it becomes 17, 16 times 1 is 16, remainder is 1, we carry 15. So it is not dividing, so we put 0. So 16 divides 3375 for 210 times, and remainder is 15. And this way we can understand that when x minus 1 to the power n is divided by x, then remainder is x minus 1 if n is odd. Here 3 is odd. Now we will go to other example for even power. Example for even power of x minus 1. And the example is, what will be remainder when 34 to the power 40 is divided by 35. Here 34 to the power 40 can be written as 35 minus 1 to the power 40. And we can apply the property here, n equal to 40, which is even. Hence, on dividing by 35, remainder will be 1. We can understand this by one easy example. 34 square, which is 2, is even, and this value comes out to be 1156. Now we divide it by 35, 1156, on dividing by 35, 35 times 3 is 105. On subtracting 105 from 115, we get 10, we carry 6, and again 35 times 3 is 105, and remainder is 1. This way we can prove that when the power is even, then x minus 1 to the power n, when divided by x, the remainder is 1. This way we can find the remainder by using the above tip. Tip 6 for remainder. Part 1. X to the power n minus a to the power n is divisible by x minus a for all values of n. Part 2. X to the power n minus a to the power n is divisible by x plus a when n is even. Part 3. X to the power n plus a to the power n is divisible by x plus a when n is odd. We can prove all these three properties. We take value of n as even and as odd. So first we take the value of n as even. X square minus a square is equal to x plus a into x minus a. X cube minus a cube is equal to x minus a into x square plus ax plus a square. X cube plus a cube equal to x plus a into x square minus ax plus a square. These are the n equal to even and n equal to odd. X square minus a square has factor x plus a into x minus a. So x minus a divides x square minus a square as x minus a is a factor. It means that when n is even, x minus a divides x square minus a square, and when n is odd, then x cube minus a cube has factor x minus a. So x minus a divides x cube minus a cube. This way x to the power n minus a to the power n is divisible by x minus a for all values of n. Now x plus a divides x square minus a square because x plus a is a factor of x square minus a square. So when n is even, x plus a divides x to the power n minus a to the power n. But when it is odd, then x cube minus a cube does not have any factor x plus a. So x to the power n minus a to the power n is only divisible by x plus a when n is even. Now when n is odd, then x to the power 3 plus a to the power 3 has factor x plus a. So x plus a divides x to the power n plus a to the power n when n is odd. This way we can easily prove the tip number 6 or property number 6 as I have proved here. We go to the next topic on numbers, arithmetic progression. The terms are a plus d, a plus 2d, a plus 3d, and so on, and last term is a plus n minus 1 into d is said to be in arithmetic progression. Here a is first term and d is common difference, and to basic formula for finding the nth term and sum of n terms. The first formula is nth term equal to a, which is first term, plus n minus 1 into d, where d is common difference, and sum of n terms. This is equal to n by 2 into 2a plus n minus 1 into d. This can also be written as n by 2 into first term plus last term, as 2a plus n minus 1d can also be written as first term plus last term. Now we will understand these two formula by two quick examples. 1 plus 4 plus 7 plus 10 is 1 AP. Here 1 is first term and 4 minus 1, which is 3, is common difference. If we go on adding 3 to the terms, then we get the next term. If we add 3 to 1, we get 4. If we add 3 to 4, we get 7. If we add 3 to 7, we get 10. And so on, we can get the terms. If we have to find the 12th term, then 12th term will be, I write T12, term 12, equal to 1, which is the first term, plus n minus 1, which is 12. Here value of n is 12. 12 minus 1 into common difference is 3. So this is 1 plus 11 multiplied by 3. This is 33. And 33 plus 1 is 34. This way we can find the 12th term or nth term. Now if we have to find the sum of 12 terms, then the Formula is n by 2 into 2a plus n minus 1 into d. Here n is 12, so we can write 12 divided by 2 into 2 times 1 as a is 1 plus n minus 1, which is 12 minus 1 into common difference d is 3. This is equal to 6. N by 2 is 6 into 2 multiplied by 1 is 2 plus 12 minus 1 is 11. 11 into 3 is 33. If we add these two, then we get 35 into 6, which is 6 multiplied by 35. And 6 times 35 is 210. So sum of 12 terms is equal to 210. This way we can use this formula and we can find the nth term or sum of n terms. For fast calculations in numbers, we should memorize or we should remember the 5 sequences. The first one is sum of first n natural numbers is given by 1 plus 2 plus 3 plus 4. These are the numbers up to n is equal to n plus 1 upon 2. Second sequence is sum of first n odd numbers, 1 plus 3 plus 5 plus 7, and it goes up to 2n minus 1. This is equal to n square. The third sequence is sum of first n even numbers, 2 plus 4 plus 6 plus 8 up to 2n equal to n plus 1. The fourth one is sum of squares of first n natural numbers, that is 1 square plus 2 square plus 3 square plus 4 square up to n square equal to n into n plus 1 into 2n plus 1 upon 6. The fifth sequence is sum of cubes of first n natural numbers, 1 cube plus 2 cube plus 3 cube plus 4 cube goes up to n cube equal to n plus 1 upon 2 whole square. We can keep in mind that sum of first n natural number is n plus 1 upon 2 and cubes of first n natural number is just square of it, that is n plus 1 upon 2 whole square. This way we can easily keep in mind and memorize it. We go to the next topic, geometric progression. A sequence having terms a into r, a into r square, a into r cube, a into r raised to power 4 and so on is in geometric progression. Here a is first term and r is common ratio. The first formula is nth term. N term can be found as a into r raised to power n minus 1. The next formula is sum of n terms. This is equal to a into r raised to power n minus 1 upon r minus 1, where r is not equal to 1. We have to remember that in all geometric progression, the common ratio r is not equal to 1. Otherwise, it will become a constant series. Next is sum of infinite GP or geometric progression when 0 is less than mod r is less than 1 is equal to a upon 1 minus r, where r is a fractional number. In between 0 and 1, like 1 upon 2 or 3 upon 4 or 1 upon 3, or in decimal number in between 0 and 1, then this formula is applicable for all infinite series. We learn the use of formula by one example, 1, 2, 4, 8, 16. This is a GP or geometric progression where a is 1 and common ratio is 2. If we go on multiplying each term by 2, then we get the next term. As when we multiplied 2 to 1, we got 2. And again we multiplied it by 2, then we got 4. And we multiplied 2 again to 4, then we got 8. And then 16 and 32 and so on. So if we have to find the 8th term, then 8th term equal to a is 1 into r is 2 and n minus 1 is 8 minus 1 is 7. 2 to the power 7 is 128. So this becomes 1 multiplied by 128 is 128. So this way we can get the 8th term. Now if we have to find the sum of these 8 terms, then sum is s equal to 1 is your first term into 2 to the power 8 minus 1 upon 2 minus 1. Here 2 to the power 8 is 256 minus 1 is 255. So this is 255. This is 1 multiplied by 255. So I have not written 1 upon 2 minus 1 is 1. So this is equal to 255. This way we can use the formula for finding the sum of the geometric progression. We must memorize few basic algebraic identities or basic formula. The formulas are given as, first formula is a minus b whole square equal to a square plus b square minus 2ab. Second formula, a plus b whole square equal to a square plus b square plus 2ab. Third formula, a plus b into a minus b equal to a square minus b square. This can also be remembered as a square minus b square equal to a plus b into a minus b. Fourth formula is a plus b whole cube. This is equal to a cube plus b cube plus 3ab into a plus b. Fifth formula is a minus b whole cube equal to a cube minus b cube minus 3ab into a minus b. Sixth formula is a cube plus b cube. This is equal to a plus b into a square minus ab plus b square. Seventh formula is a cube minus b cube equal to a minus b into a square plus ab plus b square. Eighth formula, a plus b plus c whole square equal to a square plus b square plus c square plus 2 into ab plus bc plus ca. Ninth formula, a cube plus b cube plus c cube minus 3abc equal to, in first bracket, a plus b plus c into, in second bracket, a square plus b square plus c square minus ab minus bc minus ca. And in this formula, if the sum of a plus b plus c equal to 0, then this is equal to a cube plus b cube plus c cube equal to 3abc. We must remember all these formula. These are very helpful in solving some numerical questions, and if we memorize it and use it, then the calculations and some questions becomes very easy. Here completes this video. Please memorize all the basic details and formula given in this topic, and if you will remember all these formula and details, it will be very easy for you to solve the question on numbers. We are going to solve many questions on numbers in next few videos. Please like, share and subscribe to this channel, and don't forget to press the bell icon to get the latest notifications. Thanks for watching.